As promised, this section is, once again, estimating the population mean. The difference between this section and the last section is this time sigma, the population standard deviation, is not known. Sigma is unknown. And the requirements to use the techniques of this section is exactly like the last section. The sample is normally distributed, or n is bigger than 30. As long as one of those two or both of those conditions are met, you can use this technique. Here we use the T table. T is x bar minus mu times the square root of n over s. Now, in your textbook, it's going to say it's s divided by the square root of n. But just like with dividing fractions, if you have 2 divided by 3/4, whether this top number is a fraction or not, you keep it the same way. You change division to multiplication, and you flip over the bottom. You flip over the bottom. Oh, you mean I keep the top the same, and I change division to multiplication, and I flip this over, and I get square root of n over s. But that is exactly what I have here. The square root of n ends up in the top. In my opinion, it's a lot easier to know the formula that way. And the margin of error, something we're going to use a lot, is equal to t sub alpha over 2 times s over the square root of n. The confidence interval is just like it was in the last section. It's x bar minus e is less than mu, which is less than x bar plus e. That means mu is in between these two values. If somebody tells me this, somebody tells me that, I do not think, oh, 2 is less than x, which is less than 7. Because that has no meaning to me. And trust me, it has no meaning to you as well. But what does have meaning is that x is in between 2 and 7. Now you know what x is. Oh, it's between 2 and 7. Might be 3.8, might be 6, might be 1.9, might be the square root of 5, but it's not 11. It's not 11.3, it's not 1.8. Why is it not 1.8? Because between 2 and 7 is not 1.8. 1.8 is not between 2 and 7. X is in between 2 and 7. And it does not include the endpoints. So like I tell my students, just like when you see a plus symbol, it means to add, and a multiplication symbol means to multiply. When you see this, that's the symbol for mu is in between. Mu is in between 3.7 and 4.9. That has a lot of meaning to me. Mu is in between this number and that number. To say that 3.7 is less than mu, and mu is less than 4.9, it's not wrong, but I doubt you ever fell for that. Okay. So let's do a problem. All right. We'll try to keep what we have up here. Suppose a random sample of birth weights of 186 babies. So a random sample of birth weights of 186 newborn babies. So n is 186. Has a mean. Well, that's the sample mean, because 186 isn't all the babies. Besides, it's a random sample. Had a mean of 3,103 grams. So you take a random sample of 186 babies, and you record their birth weights. And the average turned out to be 3,103 grams. With the standard deviation, so that's the sample standard deviation, of 696 grams. Now you want to construct a 95% confidence interval. You want a 95% confidence interval, confidence interval estimate of the mean weight for all newborns. You want to construct a 95% confidence interval estimate for the mean weight of all newborn babies. Okay. So we use, to do that, you're not going to find mu, but you need to know x bar and e. You need to know x bar and e. Well, how nice. We have x bar, so we need to find e. Well, here's a formula to find e. So we know S, that's 696 grams. We know N, that's 186, so we can find the square root of N. What we need to find is T sub alpha over 2. Well, alpha over 2 over 2. Alpha is 1 minus the level of confidence, which is 95% or 0.95. Well, that gives you 0.05 over 2, which is 0.025. Now, let me be very clear. When sigma is known, we use the z-table. When sigma is unknown, and its standard either is normally distributed or n is bigger than 30, we use the t-table. If sigma is known, the requirement is the sample is normally distributed or n is bigger than 30. The same requirement are for both, whether sigma is known or unknown. But if sigma is known, we use the z-table if the requirement has been met. If sigma is unknown and the requirement has been met, we use the t-table. Now, using the t-table, since it's not the z-table, it's a little bit different. The t-table talks about degrees of freedom. The degrees of freedom is always n, 186, minus 1, which is 185. Now, on the left side of their t-table, you have numbers. And my table has all numbers from 1 to 20. Then it does some for 30s and a couple for 40s, 40 and 45, 50 and 55, 60, 65. Eventually it hits 90. Then it's 100, 200, 300, 400, 500. This number is closest to 200, at least on my table. I'm pretty confident it is the same on your table. So you go to 200, and what you want to do at that point is decide which top number to use. Since we're doing the area in a two-tailed test, and we want, let me just look for a moment on the board, we want a 95% confidence interval. So in the middle here, 95%. That leaves 5% left over. 2.5% goes here, and 2.5% goes here. 2.5 just happens to be 2.5% just happens to be 0.025. So we go to two-tailed test. We look under 0.025. Oh, excuse me. I mean, we can do what I just said, but it's easier not to. Since we have, what am I doing here? There's no need to divide by 2 here. Okay, the two tails add up to 5%. So you go to the top heading that talks about area and two tails, and you look under 0.05, and you go down to 200, and you get 1.972. 1.972. For the record, do they have 0.025? Yeah, they do. If you looked up the area in one tail, which would have been 0.025, and you go to the one tail, go to 0.025, and you go all the way down to 200, you'll see the same exact number. So now we have the T number. 1.972 is T sub alpha over 2. Let me erase this. E is equal to T sub alpha over 2, 1.972 times S, which, looking in the bottom left, is 696. 696. And you divide this by the square root of n, and again, the bottom left, n is 186. Don't forget to take the square root of that. If you happen to crank through those numbers, you would get that E is approximately 100.64. So we just want to add X and E and subtract X and E. And once we do that, we just write up the answer. Some number is less than mu, which in turn is less than some number. The number in the right is going to be X bar plus E. Number to the left is going to be X bar minus E. And we know that X bar is 3103. And if we take away E, which is 100.64, I suspect we will get 3002.36. So 3002.36 is less than mu. And if I add these same two numbers, I will get 3203.64. Just add X bar and E. And you can be, with the 99, you can be 95% confident that if you survey 186 babies, that the mean will be in between 3002.36 grams and 3203.64 grams. You can be 95% confident that this will be the case. Okay, let's try one more. This time, I'm going to apply for credit. And as pretty much all of you know, there's something called your credit score. If you have a good credit score, a better chance of getting the loan. Lower credit score, lower the chance of you getting the loan. Higher credit score, lower interest rate. Okay, so when consumers apply for credit, the credit is rated using something called the FICO score. So now, suppose that we have the credit rating for 16 randomly selected people. And it has a mean of 660 and a standard deviation of, say, 95. 95 points. And we want to construct a 99% confident interval for the mean rating or the mean FICO score, the credit rating scores of all applicants for credit. So these 16 people applied for some credit. Okay, and they were randomly selected credit applicants. And they had a mean score, mean FICO score, or FICO score of 660, and the standard deviation was 95. Now we want to construct their confidence interval for the mean FICO score for all applicants in the entire population. Now, that population can be restricted. It can be population of college graduates, recent college graduates, people who earn over $120,000. It can be people who earn less than $25,000. You decide what the whole population is, and then take a sample from that. The sample is 16. Okay. So remember, so you need to know x bar minus e and x bar plus e. That is, you need to know x bar and e. Well, we are given x bar. The sample has a mean of 660. So we need to find e. E is t sub alpha over 2 times s over the square root of n. So we need to find alpha over 2. Now, since this is a two-tailed test, and let me just say something. Okay, well, since we only have a sample size of 16, in order for me to do this, I have to say assume the sample is normally distributed. So it did satisfy one of the two criteria. To use these techniques for the last two sections, you have to have a sample size of bigger than 30, or it has to be normally distributed. The sample must be normally distributed. So we're okay. So I want a 95% confident interval. That is, there's 5% left over. So the two tails is 5%. N is 16. So the degree of freedom is n minus 1, which is 15. So on your t-table, we're using the t-table because sigma is not known. The true population, their standard deviation of the whole entire population is not known. So we don't know sigma. That means we use a t-table. Okay, so you go down to, under degree of freedom, you go to 15, which I bet on everyone's table there will be a 15. Then you go across until the number under the area in two-tailed test is 5% or 0.05. and I get 2.12. I get 2.12. That is T sub alpha over 2. The only problem is that I was looking at 95, and sorry, but it's a 99% confident interval. Sorry. So it's 0.09, and what's left over is 0.01. So you go there, the degree of freedom is 15, and you look across at 15 until the number underneath the area in two tails is 0.01. And that gives you 2.947. 2.947. Okay, so now we're ready to get E. The whole job is to find E. T sub alpha over 2 is 2.947 times S, which is 95. And then you divide this by the square root of n, where n is 16. I mean, if you know that's 4, just hit divide by 4. And it turns out that if and when you crank out these numbers, you get just below 70. You get 69.99. That is the value for E. So now you have to do x bar minus E and x bar plus E. X bar is, the mean is 660. So x bar in E. X bar is 660. E is 69.99. If you happen to subtract these two numbers, you would get, I can do this, you get 590.01. That's when you subtract. If you happen to do x bar plus E, x bar is still 660, E is still 69.99. If you add these, you get 729.99. You know what? Mu is right in between them. You just have to add x bar and E and subtract x bar. You have to compute x bar minus E. And 99% of the time, the true mean will be in between those two numbers in the bottom, 590.01 and 729.99. Now, right before I finish, I'm going to give you a nice little flow chart that you really, really need to know in order to do well in these type problems. You need to know which technique to use. Z-score, Z-table, T-table. So here's a flow chart. First question you ask yourself is sigma known. And of course, you're going to respond with a yes or a no. If it turns out that it's yes, then you have two questions to ask. Well, then you have a question to ask. Is the population normally distributed? Either you will say yes or you will say no. If you say yes, then you use normal distribution. That is the Z-table. Is the population normally distributed? And you say no. Well, then you have to ask yourself yet another question. Is n greater than 30? And if your answer is yes, well, then you use normal distribution. If your answer is no, you use other techniques, which I guess in some way, fortunately for us, is something that is beyond the scope of this book. So if sigma is known, then you have, so if sigma is known, yes, then you have to decide if it's normally distributed. If it is normally distributed, you just use the standard normal distribution techniques. If it is not normally distributed, don't worry so much. If n is bigger than 30, you use normal distribution techniques. If n is not bigger than 30, you say you can't be done, beyond the scope of the book. Well, is sigma known? You may say no. You may actually say no. Okay, and that's the section we are in right now, right here and now. Okay, so you have to ask, is the population normally distributed? And if you say yes, then you use t-distribution. That is the t-table. If it's normally distributed, use the t-table. If you say no, it is not, the population is not normally distributed, then you need to ask yourself a different question. Same question that we did over here. Is n bigger than 30? Should have a question mark after that. Is n bigger than 30? If the answer is yes, well then you use the t-distribution. If the answer is no, you're beyond the scope of the book. Use some other technique. You should know this like you know your name. Is sigma known? Yes. Oh, is the population normally distributed? If it is, yes, just use the z-table and the formula associated with that. If the answer is no, it is not normally distributed, then you have to decide if n is bigger than 30. If it is, you use the z-table. If it isn't, you're on your own. If sigma is not known, that's the t-table. Is the population normally distributed? If it is, then use the t-distribution, the t-table. If the population is not normally distributed, then you have to decide if n is bigger than 30. If n is bigger than 30, you simply use the t-distribution, t-table. If it is not bigger than 30, you use another technique. So, unless your teacher tries to trick you where it's not normally distributed and n is not bigger than 30, you don't have to worry. If you know n, you use z. If you don't know, excuse me. If you know sigma, you use the z-table, the z-distribution, the normal distribution information and formulas. If you do not know sigma, then you use the t-distribution. Sigma is known, z-distribution, normal distribution. If sigma is not known, you use the t-distribution. You need to know that. You need to know the formula associated with them. Okay, good luck with this.